This conference will now be recorded.
All right, guys. So we got this minimum spanning tree to begin with, right? And we'll see what and all is the minimum spanning trees. What are the various algorithms which we can use and come out with the minimum spanning trees. So we had a very small discussion in our previous sessions when we were doing the DFS and the BFS approach. So what is a graph? Graph is typically a non-linear data structure, right? And we define a graph as a set of edges and vertices. So we can use it to implement some social networks like Facebook or LinkedIn, right? So this can be even used for electrical wiring, right? Where you can say different poles, how are they going to be connected? So typically when we see how an MNC works, right? So there is an attendance management process. So there is an RFID tag given to every employee in the companies. So wherever the employee is going, so he has to punch in the tag, right? So we can trace the path of the employee where and all he is going. So that's like one again graph application. So GPS or the maps are again one of the beautiful implementations, right, with the graph as a data structure. So in the graphs, we got vertex, edge. So if you see this vertex 1, 2, 3, 4, and 5, and when you see the edge, it's a path which is connecting two vertices. So in every graph, you can have a start vertex and end vertex to define that, okay, from here we will start to traverse and here we'll be finishing our traversal, right? Now, there may be graph which can be referred to as directed. Directed means you got directions, right? And in an undirected graph, it is bidirectional. The same direction from 1 to 2 is also 2 to 1. But in case of a directed graph, so 0 to 1 is one direction, but 1 to 0 is no direction, right? In case of a directed graph. Now, there is something known as cyclic graph. So a cyclic graph is the one in which you can see this 0, 2, and 3 forming one cycle, right? So in this undirected graph, you cannot see the cycles. Now, it is not like that the cycle can be there in a graph which is directed. It can be directed or undirected, right? So there are cycles available in the graphs. So you need to write your very first program to detect the cycle in a graph, right? So I'm just gonna come here and put it across. So let us write this new Python file, session 34. So this is our graph, right? And this graph will certainly look like your this part here. If you see, guys, it's gonna be a directed weighted graph. So this we did in our last session. So it's like both now, which is implemented either undirected or directed, right? But it's a weighted graph. So you got an edge, you got a vertex 1, vertex 2, and the weight. So in this graph, you have the cycles, right? So even if there is any cycle, you need to detect it and you need to tell us what is the cycle in your graph and is your graph cyclic or not. So the assignment I'm writing below, right, in this session number 34. So please implement a function is cyclic which must return true or false. So I'm going to have this function called define is cyclic. And yes, I gave you this assignment for adjacency matrix, right? So you have to come up and do that as well. So implement this function to detect any cycle in the graph. So guys, is this clear to everyone? So what is this assignment all about? Can I get a smiley from all of you? All right, so Namnoor says, give us one hint to detect the cycle. So Namnoor, in case you are in the graph, right, you start your BFS or DFS approach, right? So you go from 0 to 2, then you go from 2 to 3, and then you go from, let's say, 3 to 0 again, or 0 to 3 again, right? So there may be a node which you are revisiting again, right? Or at the same time, what I can do is I can get these three edges, right? Edge 1, edge 2, and edge 3. So this edge 1 is 0 to 2, then 2 to 3 is another edge, then 3 to 0 is another edge, right? So once you got these three edges along with the vertices, you can very easily check that whether it's a cycle or a not, right? And yes, you can use the properties of your set data structure. You can work on the intersections, the unions, right? How you can actually come up and see. So good to go, Namnoor, with the hint. And guys, can I get an acknowledgement as a smiley from all of you? Is this assignment clear to everyone? So Shivam, good to go? All right, guys. So what are these spanning trees now? So for an undirected and a connected graph, right? So spanning tree T is the subset of the graph G, which contain all the vertices and will not have a cycle. So now I hope you understand why I have given this assignment, right? So if you see, there is an undirected graph, right? So we are going to have a spanning tree where you have all your vertices, and every vertex is connected to one vertex without forming a cycle. It means you have connections, and that to only one single connection, one single edge from one vertex to the other vertex, right? So guys, let's see the conditions to create a spanning tree. Now, a graph should be connected. That's the first part, right? You cannot have a spanning tree if your graph is not connected. There may be that you have some vertices lying here and there, but they are not connected to each other, right? So a disconnected graph does not have any spanning tree, right? As we cannot span it to all the vertices. And a graph should have at least more than three vertices. If you have only three vertices, right, it won't be they may be connected to each other, they may not be connected to each other, but you won't be able to create a subset of three vertices, right? Now while creating a spanning tree, you are trying to work on this fundamental called minimum cost spanning trees. We understand that we have directed trees, undirected trees, we have weighted, or we have no weights on the edges or on the paths. But when you have weighted trees, whether directed or undirected, now that won't be a concern for us, much of a concern for us as of now, right? But when you have these weighted graphs, so you can try writing multiple spanning trees out of these weighted graphs. Now for example, you can touch down your four vertices in this manner, or four vertices in this manner, right? So it's up to us that how you span across. But the only thing is this, that both of your, I mean to say, all of your vertices should be touched on. Now, every spanning tree can have a cost. Cost is addition of the weights on your edges, right? So if you write a spanning tree, there will be a cost associated with the spanning tree in case it's a directed graph. So the cost can be evaluated by adding the weights on your edges, right? So you're going to add 2 plus 4 plus 5. In the minimum spanning tree, you are trying to find particularly that kind of a spanning tree where the cost is minimalized, right? So in this spanning tree, the cost comes out to be 11. In this spanning tree, the cost is 7. So our algorithm works in finding the minimum spanning tree, which is basically the minimum cost associated with this resultant spanning tree. And your minimum cost spanning tree is basically the shortest path through which the vertices are connected to each other. So can I get an acknowledgement, guys? Is this part also clear to everyone? What is the minimum cost spanning tree? So minimum cost spanning tree is the one where we are trying to work on the shortest paths in our graphs, right? So why you would kind of consider this as a shortest graph? What can be the applications? Yes, of course, when you use Google Maps, right, the shortest path is one of the you can say major applications, right? When we would like to travel from location A to location B. Now, one more discussion kind of a query here. How do you think that we can implement graphs in hospitals? I would like to get one acknowledgement over the chat box, guys. So, what do you think? What can be the application of graphs in the hospitals, and where we would be needing this shortest path concerns or the minimum cost spanning trees in hospitals? All right, so Navnoor says that in hospital there will be multiple wards, and in case they are supposed to be connected to one nurse room, then this can be used off. Exactly. So guys, typically if you see in a hospital, a patient is transferred from one place to the other place for the various let's say tests, right? And there may be some other concerns that there have some nursing station there are some nursing stations associated to wards. So we can have these graphs where we can have the layouts of the nursing stations in the hospitals, right, as the vertices, and how are these different nursing you know rooms, or let's say the wards, they are connected. That becomes a kind of a graph, right? So how we can evaluate that from one ward, if you want to take the patient to the other ward, so what can be the minimum path or the shortest path to be followed, right? So certain applications, they do exist for the graph anywhere here and there. So computer networks is one of the major applications, right, where graphs are implemented. So these data network, right, the networking part, how the packets they flow from one router to the other router, right? Telecommunication network, so how your voice calls are placed, how this data network is being transferred. Then the transportation networks, water supply networks, electrical grids. Of course, when I say transportation network, we're trying to come up and say the maps, the Google Maps. So these are the various applications where MST is highly required. Now there are three important algorithms, right, to find the minimum spanning tree. You got Kruskal's, Prim's, and Sollins, right? So these are the three algorithms. We have even one more algorithm called the Chkastra algorithm, right? That is some traditional algorithm which I think is not that challenging for anyone to understand. But at the same time, these three algorithms, we're gonna begin with Sollins today, right? So Sollins algorithm is going to be one of the most easiest implementation out of these three to begin with, right? So Sollins algorithm is also known as Borucka's algorithm. It is used to find this minimum spanning tree. And let's see what exactly this algorithm will do for us. It's a greedy algorithm first of all, right? And when I say greedy algorithm, so there are some algorithms which will solve the problem by hook or crook. So that's how we say the greedy algorithm approach. So we are going to check all the possibilities of a given problem, right? Then at the first stage, we select that which can give us the optimal solution. And at the next stage, always choose the next piece that offers the most benefit. So greedy algorithm is an algorithm that builds up a solution step by step by checking for the optimization. But at the end of the day, right, so we have to follow the solution. So how are you going to work on the Sollins algorithm? So guys, you see the left hand side is one of the graphs. So we need to create a minimum spanning tree which is to your rightmost. So if you see 0 to 5 is 10. We didn't connect 0 to 1 because we know from 0 to 1 it's 28. So the cost will be more if you connect 0 to 1, right? If you connect 0 to 5, so cost is 10. So 5 may be connected to 4 by 25. Then 4 is connected to 3 by 22. 4 is not connected to 6 by 24 because 24 was greater than 22. Then 3 is not connected to 6 because your 18 is greater than 12. So 3 got connected to 2. 2 got connected to 1. Now 1 is not connected to 0. 1 will be connected to 6 because 14 is less than 28. So typically, when you are trying to write this Sollins algorithm, you are working on the adjacent vertices and you choose that vertex who has less weight associated to it. So guys, we are going to highlight the cheapest outgoing edges from all the vertices first, right? So that should be our very first approach. Thereafter, we will choose the cheapest edge for each vertex and we keep on repeating this algorithm for each subgraph, right? And let me try to come up and give you one small, approach on the same algorithm here. Small write-up which I'm going to give you. So you need to write this function called define Sollins, right? I'm going to give a pass here. So how your Sollins gonna work? So you implement your Sollins on the same graph, right? So first of all, you write every vertex. So I'm gonna write this vertex here as 0, then 1, 2, 3, 4, 5. So we got these 6 vertices, right? So if you see, you got these 6 vertices here, 0, 1, 2, 3, 4, 5, and 6. Now the next part for us is to identify the edge which is going to be the minimum weight from every vertex, right? So when I come to this 0, so when you see the 0, I find 0 to 5 and 0 to 1 as the neighbors, right? So 0 to 5 and 0 to 1 will be the adjacency list, but 0 to 5 is going to be the optimal cost. So I'm going to say for 0, I got 0 to 1 as edge, right? So this is vertex, and this is going to be cheapest edge to other vertex. So coming here, the next guy is 1. So 1 has the cheapest edge to 6. 1 is connected to 0, 1 is connected to 2, 1 is also connected to 6. So I'll say for 1, it is going to be 1 to 6. Then let's write the 2. So guys, you have various edges, but you are finding the cheapest one, right? So 2 can be connected to 1, 2 can be connected to 3, but you got this 2 to 3 as cheapest edge. So you're gonna write 2 to 3. Let's go with this guy called 3. So for 3, it's gonna be the cheapest edge over here for us is again going to be this 2 to 3 only. So in an unidirectional graph, it won't matter for us, right? Either 2 to 3 or 3 to 2, it's the same edge. Guys, can I get a smiley here? So for 3 also, it is 2 to 3. If you see here, right? So this is going to be the cheapest edge because 3 to 6 is 18, then 3 to 4 is 22, right? So you got this as cheapest. Now you go to 4. So in the case of 4, we got 4, 5, 4, 6, 4, 3. So it's 4, 3, which is the cheapest edge. Thereafter, you go to 5. So with the 5, it's 5, 4 or 5, 0. Right, guys? So for the 5, it is either 5, 4 or 5, 0. So for 5, it is going to be 5, 0 as the cheapest edge. It's either 0 to 5. So sorry, my bad. For 0, it's gonna be 0 to 5. I just wrote wrong here. So 1, it is 1 to 6, right? And for 6, guys, it is going to be 1 and 6. So let us highlight these edges and see if it is correct or not. All right, so anyone with any query here? So just give me a moment, guys. I'm gonna do a small highlighting here. So 0 to 10, you got this edge. 0 to 5, sorry, I got this edge. Then 1 is going to be connected to 2, not to 0. Then 2 is going to be connected to 3. 3 is going to be connected to 2 again. So for 2, 3 and 3, 2, it's gonna be same, right? Let's see here, 2, 3, 2, 3, it's gonna be same. Then next for us is going to be for 3, it's gonna be 2, right? And 4, it's either 5, 3 or 6, right? So it's 4 to 3. Then for 5, it's gonna be 0, 5 and not your 5, 4. So how is this graph now created, guys? Let's see. Now this graph is typically connected in this manner. So you got some components in your graph. So this is one component in your graph, and this is another component in your graph. So these two are not connected. Can I get a smiley from all of you? So as of now, what we see is, and this guy is left out independently, I think, as of now, not connected to everyone or anyone. So we got three different components out of them. So if you will look out for this 0, 1, 2, 3, 4, 5, 6, right? So these vertices, they form these kind of components, individual components, right? So I will write that this is your component number 1, this is your component number 2, this is your component number 3. A smiley awaited from all of you as an acknowledgement in case we are good to go. Now you need to connect these components, right? So these components need to be connected on the minimum weighted edge. So what we see is the minimum weighted edge for these components can be connected now. So how it can be connected? So component 1 and component 2, they can either be connected with this 28 or they can be connected with this 25. So we connect the component 1 and the component 2 with this minimum path called 25. So 5 and 4 makes a connection, to be precise. Now this component 3 can be connected to this component 2 either by 1 or by 4 as the shortest path, right? So this is the shortest path. So your component 3 can be connected to component 2, and this is going to be the path which we have to confirm. So guys, can I get a smiley? So overall, this becomes your minimum spanning tree. Can I get an acknowledgement from all of you? I would like to get a smiley in case we understood the entire algorithm. All right, guys. So now you need to write the program. In order to fulfill the same, you need to write the program, correct? And your program shall result in this tree at the end of the day, minimum spanning tree. So the very first thing is that you list your all the edges, I mean all the vertices with the cheapest edge by weight, right? So once you do this, so thereafter you need to find that which and all components are supposed to be connected to each other. So how you will find that? My question goes like, you wrote this, so this can be found, right? So in the adjacency list, who and all are the shortest path, that you can find, right? That you can sort. So if you will see here, so you're maintaining this list, right? This list over here is going to have this weight and the vertex. So you can sort this list, and once you sort this list, you get to see that the 0th index will be the edge with the shortest, the least weight, right? So that's the first step which you can do. The second step is how you create the components. So I'm writing these steps here. Create components. So number 1, fetch all the cheapest edge to other vertices by weight. Once you do this, then create components. Your C1, C2 and C3 were 3 components. So guys, in your first component, you had this 0, 5, right? So this 0 and 5 was there in the first component. You had this 0 and 5 in the first component. In the second component, you got this fellow called 1, 2, 3, and 4. And in the last component, you had this guy called 6. And finally, join the components on the basis of minimum weighted edge. And finally, you got this minimum spanning tree, right? So you need to come up and give this minimum spanning tree. So what and all are the vertices, what and all are the edges available in your minimum spanning tree? So in the minimum spanning tree, you got 0, 5, 4, 3, 2, 1, and 6 connected in this manner, right? And if you will add the weight, it will be always the least cost in your tree, in your graph. So guys, can I get a smiley from all of you once again? So this is what you need to do for the day, right? And you need to fetch all the cheapest edges to the other vertices by weight, create the components, join the components based on the minimum weighted edge, right? And if you will look out for this assignment here is cyclic. So this you can do later, right? The first one is to code the Sollins algorithm. Then the next one is that you write is cyclic. So code wise, I have given a hint that how you can find the cheapest edges. You need to sort your adjacency list. You will get the sorted arrangement. The zeroth index will be the shortest, the least weight. Once you create that, then you need to write your components out of these. Correct? So 0 and 5, they make one component for us. Then 1, 2, 3, 4. So your 1, 2, 3, 4. So this 3, 4, right? 1, 2, 3, 4, right? So they make another component, and this 6 alone was kind of 6 left out for us. So you create components, and then how the components can be connected to each other. So the code I'm going to push here, guys, to the GitHub link. So anyone with any query here? Can I get an acknowledgement from all of you? So this screenshot I will share with all of you, but at the same time, you can take any graph to begin with. So in our case, you have this directed weighted graph. So you can try working on this graph, right? So you can make it undirected. You can consider it to be as undirected, and you can try creating the minimum spanning tree out of this. Okay. So for example, 0 may be connected to 2. Then 2, you can consider this to be your bidirectional. Then 2 may be connected to 1 as in the shortest path. Then 1 may be connected to 3. So shall I just try to highlight this? So just give me a moment. So 0 will be connected to 2, right? And 2 will be connected to 1, because this is the shortest path coming out here as 50 and 50, right? 1 will be connected to now either 3 or 4. So choice is yours. So you can choose any one in case of this situation. So let's say it's connected to 3, and 3 is connected to 4. So once this is done, you have touched every vertex. So this is touched, this is touched, this is also touched. So once you touch every vertex here, right, so this becomes your minimum spanning tree. Can I get a smiley from all of you? So you can work in the same graph, consider this graph to be undirected, and thereafter you can write your program, or you can work on any graph of your own choice as well. So this will be all for the day, right? And it's gonna be Sollins algorithm implementation today. So it's been a long time that you guys haven't code as in some algorithmic challenge. So this is what I have given as an assignment for all of you. All right. Once you do this, once you have solved this problem statement in your Google Maps example. So we got this Google Maps example at the same time, guys, right? So here in the session number 33A, you can try implementing your shortest path with the algorithm called Sollins. All right, so Gurlivleen, Lavish, Malika, Navnoor, Prab, and Shivam, guys, anyone with any query here? So this is going to be all for the day, right? So we typically have this 1 hour sessions in the morning, 9 to 10. Now it will vary. They may sometimes go from 9 to 10, 10:15, 9 to 9:30. Depends exactly on the content, right? Okay, guys, thank you. So this will be all. Have a wonderful time ahead. Happy coding, and make sure that you code the algorithm well. Thank you, guys. Thank you so very much. Okay, bye bye.